Okay, YouTube, in this last video we're going to talk about the relationship between the factors of a function and the zeros of a function. So we say due to the factor theorem basically says that if x equals k, if that's one of our zeros of our function, then x minus k, it must have been one of the factors of the function. Because remember that if we have some polynomial function that we could write as, maybe something we divided it by times the quotient we got, and there's no remainder, which means x minus k is a factor, then setting x minus k equal to 0 is always going to imply, setting that factor equal to 0, it's always going to imply that x was equal to actually positive k. So what this means is essentially is that if we know all of the zeros of a function, then we could rewrite all of its factors by thinking backwards here, and then we could actually go rewrite the function having those zeros. So let's take a look at this example here. It says write the equation of a polynomial function of third degree. So we want a third degree function. We say n usually represents our degree. I'm going to write n as 3 here. But we say having zeros, x equals -1, +1, and 2, and then graph the resulting function to verify that it has the proper zeros. So let's take a look at what this would imply. If x is equal to -1, then we'd say, well, then what must have been the factor that is associated with this? And resetting this equal to 0, you could see that x plus 1, that must have been the factor, or at least the factor that gave you this 0 here for this function. So if x plus 1 is our factor there, we could say, well, then what was our factor for this 1 here? Saying that x equals 1, of course, implies that x minus 1 is its factor. And then also, of course, if x equals a +2, then x minus that +2 is its factor. So what we want to do here is this. We want to write a third degree polynomial function f of x. And what I know is this. I'm going to leave my leading coefficient as 1. But I'm going to say that x minus our zeros here, and we're just going to fill those in. We can write all polynomial functions in this way. So we can say -1 here, +1 here, and +2 here would give us a polynomial function that really is x plus 1, x minus 1, and x minus 2. So now I get plenty of people that just go ahead and write it this way first, but you have to understand that we're always going to say that it's x minus our zeros, where our zeros in this case are like some k1, k2, k3. It's x minus k1, x minus k2, x minus k3. So we fill these in. We want to say, well, what is the polynomial? Well, what we're going to do now is multiply and simplify. Multiply and simplify. So let's go ahead and start with, in this case, since it doesn't matter what order we multiply factors in, I'm going to multiply these two conjugate pairs first because I know I get a difference of 2 squares. As a matter of fact, x plus 1, x minus 1, I'll even write it that way. I say I get this thing squared minus this thing squared, all of that, times the x minus 2 that I'm just going to bring out back here. So we'd say x would go on the front and 1 would go on the back. So I would say then I get x squared minus 1 squared, so minus 1. We say times x minus 2. So now we'll FOIL this here and see what we end up with. We get x cubed minus 2x squared minus x plus 2. And so this is our polynomial function, and we're saying that it's a third degree thing because we took 3 first degree things and multiplied them together. And it should have these red values here, 1, -1, and 2 as zeros. And so we're going to go check this out here. So we say x cubed, let me get this out of here. We have x cubed minus 2x squared plus x minus 2. No, minus x plus 2 maybe. I have to go back and check here. We have minus x plus 2, indeed. Okay, so we have this third degree polynomial, but you look at the zeros that we get here. These are exactly the zeros that we wanted it to have in the first place, okay? So you can see how having the zeros of a function allows you to always work backwards to write the factors, and if you know the factors, we can re-multiply them, which I don't like to do, but we can, and get the original polynomial that gave us those zeros in the first place. So let's look at this last theorem here, which goes kind of hand in hand with what we've just mentioned with the factor theorem, but it says the Irrational Conjugates Theorem. And it says let f be a polynomial function with rational coefficients, and let a and b be rational numbers such that the square root of b is irrational. And then we say if a plus the square root of b is a 0 of f, then a minus the square root of b is a 0 of f. So basically, we're going to say a couple things here. If a plus the square root of b is a 0, then a minus the square root of b is a 0. We're going to write a word here. This is its conjugate. And we're also going to note this. If, and I'm going to make this a little bit more concise, you can write it in more detail in your paper. If a plus bi, then a minus bi. And so it's kind of the same thing here. Because we say a plus the square root of bi, a minus the square root of bi, we'll let b represent any value here, but we say that complex conjugates and irrationals in general have to occur in conjugate pairs, is all this says. So we'd say writing the polynomial equation of, say, a third degree thing, we've been given the zeros here are x equals 2 and 3 plus the square root of 7. It says, then graph the resulting function to verify it has the proper zeros. Let's go write the equation of this. So we say f of x, and let's just assume that our leading coefficient is 1, but I would say because x equals 2 is a 0, then x minus 2 must have been its factor. So here's where this is going to get a little bit different this time. Notice that I'm writing in our other factors here, or x minus the 0. Also notice that we want a third degree thing, so I've written 3 factors, but we were only given one of these zeros, this 3 plus the square root of 7. So I'll be honest with you, often problems are written this way, instead of writing x equals 3 plus or minus the square root of 7, to see if you understand that they have to occur in conjugate pairs. So because I was told that 3 plus the square root of 7 is one of the zeros, I know that 3 minus the square root of 7 must be the other 0. So step number 1 is to write the linear factors that this has given the zeros. You have to be able to get to this step before we can proceed to the next step. So now what's going to go down now is just a whole bunch of algebra. So our first thing that I'm going to tell you that you always want to do is distribute the negative on your factors up here. Because the negative occurs in front of this quantified mess here, we'd say we'd really get x minus 3 minus the square root of 7. And we're also going to get x minus 3 plus the square root of 7. Okay. So from here, what we're going to do is a little bit of algebraic sleight of hand. But that sleight of hand occurs when we do this. We're going to associate this x minus 3 together. So let me put red ink here. X minus 3. There we go. Minus the square root of 7. And over here we're going to associate the x minus 3 plus the square root of 7. So you can see that we have something here where we have an x minus 3 and a square root of 7, and they're both conjugates. So this is like a minus b, a plus b. So what we can see is that if I were going to multiply these, just like in that last example where we had just a simple real number, I'm going to multiply this out to be a difference of 2 squares also. So we have this squared minus this squared, where in the first set of parentheses we're going to put in our x minus 3 part. And our second parenthesis here, set of parentheses, we're going to put in our square root of 7 part. So let's go ahead and simplify the second set of parentheses here. You'll notice that I just keep bringing down the x minus 2 in front here. So this x minus 3 squared, remember that it's a binomial expansion. We actually have to FOIL that out. And then minus the square root of 7 squared is just 7. So let's simplify this further. Sorry for my work mess here. We say x minus 2 is still out front. Over here now we get x squared minus 6x plus 9 when we FOIL this. And then we'd say that was all minus 7 here. And so x minus 2 still out front. Let's put our 9 and negative 7 together. We get x squared minus 6x plus 2. So now all of that algebra, now we can finish this off by distributing here and getting our polynomial function. So we'd say equals, now x times x squared is x cubed, x times negative 6x is negative 6x squared, and x times a positive 2 is 2x. So we say here negative 2x squared plus 12x minus 4. And so altogether we say all of this, wow, x cubed. So x squared, we say negative 6 and negative 2 is negative 8. X to the first, we say 14 of those guys, 14 x's, and then minus 4 constants. Oh man, okay, so all of this, we're going to put this into our graphing calculator here. So let me twist this out of the way so we can see what our function is here. We'll go up over here. So we were able to get f of x, having the zeros we wanted here, was defined by x cubed minus 8x squared plus 14x minus 4. And when we look at this function here, we can see that we have our zeros at 2. So now 2 was one of our zeros that we wanted here. And then we have 3 plus the square root of 7 and 3 minus the square root of 7. So taking a look at that, we can actually put that into this calculator. 3 plus the square root of 7. And I'm going to be lazy here. Control All, copy, paste, and we'll go back and make this a minus. But you can see that these two zeros here are certainly the zeros that are represented on our graph. Okay, so irrational conjugates theorem basically means, remember, that if you have an irrational zero, whether it's imaginary or not, it has to occur in conjugate pairs. And in terms of writing the factors from the zeros, that's really important that you always write x minus the 0, whether that be some parenthetical quantity like 3 plus the square root of 7, or if it's just a -2, I should probably put parentheses around that. Cheers.